Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic mechanical engineering. We'll dive into key concepts like Newton's law of viscosity, Pascal's law, Bernoulli's equation for incompressible fluids. Slide 1. Newton's law of viscosity, definition and concept. Let's begin with viscosity. Viscosity is a fluid's resistance to flow. It's a measure of how much internal friction exists between layers of fluid when they move relative to one another. Imagine stirring honey versus stirring water. Honey is harder to stir because it has higher viscosity. Now, Newton's law of viscosity states that the shear stress, tau, in a fluid is directly proportional to the velocity gradient, rate of change of velocity between the layers, and this constant of proportionality is called dynamic viscosity, mu. Mathematically, shear stress, tau, equals viscosity, mu, multiplied by velocity gradient, du, dy. Or, tau equals mu times du, dy. Fluids that obey this relationship are called Newtonian fluids. These include water, air, and most simple liquids. On the other hand, non-Newtonian fluids, such as ketchup or blood, do not follow this law. Their viscosity can change with stress or time. This law is important in predicting fluid behavior in pipes, around aircraft wings, and in lubrication systems. For engineers, it helps select the right fluid for different mechanical applications. Slide 2. Applications and significance of Newton's law of viscosity. The real-world usefulness of Newton's law is huge. 1. In lubrication systems, like in car engines, the correct viscosity oil ensures that metal parts slide smoothly without much wear. 2. In hydraulic systems, it helps engineers predict how easily a fluid can be pumped through pipes. 3. Chemical and food industries rely on it to handle thick fluids like syrups, pastes, or oils. 4. Biomedical engineering uses it to analyze how blood, which is a non-Newtonian fluid, flows through veins and arteries. 5. It helps calculate pressure drop and energy loss in fluid systems. This affects pump power requirements. 6. In aerodynamics, engineers consider viscosity to reduce drag on surfaces. 7. It also contributes to heat generation due to friction in high-speed flows. 8. Even the printing industry uses this principle to control the flow of inks. In short, understanding viscosity helps us design safer, more efficient systems in many fields of engineering. Slide 3. Pascal's law, definition and working principle. Now let's discuss Pascal's law. This law applies to fluids that are at rest and confined within a closed system. According to Pascal's law, any pressure applied at any point in a confined fluid is transmitted undiminished in all directions. Mathematically, pressure P equals force F divided by area A. Or, P equals Fa. This means if you apply a force to a small piston in a hydraulic system, the pressure generated is felt equally throughout the fluid. This same pressure can lift a much larger load if applied to a bigger piston. This is how hydraulic jacks and presses work. Pascal's law is valid for incompressible and static fluids only, meaning the fluid should not be moving and must not compress significantly under pressure. This principle is the basis for many modern machines that multiply force to perform heavy tasks with minimal input. Slide 4. Applications of Pascal's law. The practical applications of Pascal's law are all around us. 1. Hydraulic jacks used in garages can lift heavy cars with just a small effort. 2. Hydraulic brakes in cars transmit force from the pedal to all four wheels. 3. Hydraulic presses are used in manufacturing to bend or shape metal sheets. 4. In hydraulic elevators, a small motor can lift many people using fluid power. 5. Power steering in vehicles uses hydraulics for smoother control. 6. Hydraulic cranes lift heavy loads at construction sites. 7. Hospital equipment, like adjustable beds and dental chairs, also rely on this. 8. It's used in factory automation to control robotic arms or tools. 9. Everyday spray bottles and syringes are basic examples of Pascal's principle. Pascal's law shows how fluid mechanics helps us achieve more work with less effort. Slide 5. Bernoulli's equation for incompressible fluids. Now, Bernoulli's equation. It explains how energy is conserved in a flowing fluid. The equation states that in a streamlined flow of an incompressible fluid, the total mechanical energy, pressure energy, kinetic energy, and potential energy remains constant. The equation is: key points. If a fluid speeds up, higher V, its pressure, P, drops. If a fluid moves up in height, h, its pressure drops unless velocity or input pressure compensates. This inverse relation between pressure and velocity explains lift on airplane wings. Air moves faster above the wing, lowering pressure and lifting the plane. This principle also explains how venturimeter measure flow rate by observing pressure differences. It is also used in carburetors, chimneys, and spray guns. However, Bernoulli's equation assumes no viscosity, steady flow, and no energy losses, which makes it an ideal case. Slide 6. Bernoulli vs Pascal vs Newton. Let's simplify and explain the table comparing all three laws. 1. Focus. Newton focuses on shear stress and viscosity in moving fluids. Pascal focuses on how pressure behaves in static fluids. Bernoulli looks at energy conservation in a moving fluid. 2. Governed behavior. Newton's law governs how thick fluids resist motion. Pascal's law explains pressure transmission. Bernoulli governs pressure, velocity, and height relations. 3. Formula. 4. Fluid conditions. Newton's law applies to any fluid in motion. Pascal applies to static, incompressible fluids. Bernoulli applies to incompressible and inviscid, non-viscous, fluids in motion. 5. Application areas. Newton's law is used in lubrication. Pascal's in hydraulic tools. Bernoulli's in flow devices like venturimeter and airplane wings. 6. Type of energy. Newton looks at internal resistance. Pascal's law uses force-based pressure. Bernoulli's equation considers energy transformation in flow. 7. Real example. Newton, oil in gears. Pascal, car brakes. Bernoulli, jet of water in a nozzle. 8. Units. Newton's viscosity uses ns per square meter. Pascal's and Bernoulli's use Pascal, pa, for pressure. 9. Inventors. Isaac Newton for viscosity, Blaise Pascal for hydraulic pressure, and Daniel Bernoulli for flow energy conservation. This comparison helps students see where each law applies and how they differ in concepts and applications.